Hello again. This video will talk about section 6.4, where we will be finding the volume of three-dimensional solids formed by two-dimensional regions rotated around the axes, but this time we're going to be using a shell method instead of a washer or a disk method. So I want to start off by just pointing out a couple of interactive figures from the Multimedia Library in MathLab. And this first figure shows where the shell idea comes from. So you can see that we have a region here that is formed by a curve and then an interval from A to B bounding that curve. And we're rotating that curve around the y-axis, which produces this three-dimensional solid. And you can see that centered in the solid is this cylindrical shape. So what we're going to do is we're going to take a series of intervals, of sub-intervals over the main interval from A to B, and we're going to section those off in equal sub-intervals, and we're going to revolve each of those rectangles around that axis, and it's going to produce all of these cylinders where one is kind of set inside another. So if you can picture this cylinder and then another cylindrical region drawn around it and another one around it and around it, it creates what sort of looks like a shell. Let me show you the idea here in terms of taking a subinterval. So here we have one subinterval and it creates this rectangle, and we're going to revolve that particular subinterval around the y-axis, and here we have that hollow cylinder. Okay, so each of our cylinders again will be hollow, and we're going to do an infinite number of these cylinders all built around each other to create different heights. As you can see, the height of the cylinder is going to change as we go over the interval from A to B. So here we'll have the highest cylinder, and then as we go towards B, our cylinders will start to get low. So we'll have these taller cylinders on the inside, and then as we move out, we'll have a series of shorter intervals, of shorter cylinders surrounding them. Alright, so now let's take a look at some examples. And more specifically, let's start off with, let me resize my area here. There we go. Let's start off with having a better understanding of what the formula is and where it comes from. So we talked about the fact that we'll have a series of hollow cylinders in the shell method. And so I actually have a sheet of paper here, and this sheet of paper can form a hollow cylinder. Sorry, it's covering up my formulas here until I'm ready to use them. But we can create a hollow cylinder by rolling up this sheet of paper. So if I kind of dip it this way, you can see that it creates this hollow cylinder. But the idea is that when I unroll a hollow cylinder, I end up with this rectangular shaped region. So here I have the rectangle shown. And the length of the rectangle is 2 pi r, because remember, that's what created the circumference of the circle that forms the cylinder. So if I go back to my cylinder here again, alright, so there's my circle, my cylinder, and the circumference of that circle is exactly the same length as the rectangle. So 2 pi r is the length of the rectangle, and then the height represents obviously the same height of that rectangle. So in general, the area of each one of these hollow cylindrical regions is going to be found by taking 2 pi r and multiplying it by h. That creates our shell method formula. So you can see here that we're going to be finding the volume of our three-dimensional solid by taking 2 pi r, or in this case x is a better variable to use, but 2 pi r or 2 pi x, which is representative of that shell circumference, the length of the rectangle right up here. So we've got this piece 2 pi r, written as 2 pi x. And then the height of the shell will be found by taking one curve and subtracting the other curve, so that you get a total vertical distance. Okay, so we've got the circumference times the height, so that this entire expression represents the area of our cylindrical region, where if we take the antiderivative of it or integrate it over the interval from a to b, we will get its volume. So the tricky thing about the shell method is that the way that the shells are set up, or the way that the cylinders are set up, we actually are revolving around the y-axis, but then integrating with respect to x. So it is opposite of what you saw in the disc and washer methods. Same thing down here. We've got a similar formula where all of our variables are with respect to y, and we're revolving around the x-axis. All right, so let's take a look at an example. So my first example is going to be an example in which we take two curves and we revolve them around the y-axis, and we find the volume of the resulting three-dimensional figure using the shell method. So you can see that my two curves are y equals x minus x squared, which is a parabola. It's a reflected parabola because the x squared piece is negative. And then I also have y equals 0, which is a horizontal line at 0, or in other words, the x-axis. So you can see that I've rewritten that first parabola by factoring out the x. What that's going to do is help me graph it so that I know where the x-intercepts are. And then, as I mentioned here, this line is just the x-axis itself. So the first thing I'll want to do is draw this two-dimensional figure so I can picture what's happening. And it'll help me determine some of the things that I need to plug into my area function in order to integrate that and get volume. So let's take a look at the graph that I got when I graphed my parabola here with x-intercepts at 0 and 1. And so in 2 dimensions, this is the graph of y equals x minus x squared, and also bounded by y equals 0, which is the x-axis. So it creates this region right here. Kind of looks like a semicircle, but it may not be. Alright, so in order to find the volume, again, I need to find the area of the cylinder. So 2 pi r, or 2 pi x in this case, gives me the circumference of the circular part of the cylinder. And then the height of the cylinder is going to vary depending on x. And you're going to figure out that height by taking x minus x squared, or a point on x minus x squared, and subtracting y equals 0 from it. So here you can envision all of these various heights at different points or different subintervals from A to B. And so that height is going to change depending on x. So x minus x squared minus the y minus the x-axis of 0 gives me a total height for my cylinder. You can see I've also already determined my limits of integration, and that's just based on where the two curves, the parabola and the x-axis, intersect. And they intersect at 0 and at 1. So that is my interval A to B. Alright, you can see that there was quite a bit more work here in terms of actual integration. So first of all, if I subtract 0 here, nothing happens. But I also do need to distribute that x in order to create a function of several terms, a non-factored function. I pulled out the 2 pi, and when I distributed the x, I got x squared minus x cubed. Alright, so from 0 to 1, we're integrating this area function for this cylinder, or for an infinite number of cylinders over this interval from 0 to 1. All right, if, as always, you want to stop and test your knowledge of integration, you can certainly pause here and see if you can get the correct volume. Looking at the solution, of course I need to find the antiderivative of each piece of my function. So if I find the antiderivative of x squared, here you'll see I got x cubed over 3. And then the antiderivative of x cubed is x to the 4th over 4. Don't forget about your 2 pi. You pulled it out, but you still have to factor it back in. And then, of course, using the fundamental theorem of calculus, I'm going to plug in my upper limit and my lower limit and subtract the two values. So if I plug 1 into this function, I'll get 1/3 minus 1/4, and then I also need to multiply that by 2 pi. And then if I plug 0 in, I'm just going to get 0. So you can see I have that all here. And 1/3 plus 1/4, 1/3 minus 1/4 becomes 1/12, multiplied by 2 pi gives me pi over 6. So that should be the volume of the solid that's formed when we rotate this particular two-dimensional figure around the y-axis. So remember, we're going this way around the y-axis, and it's creating these shells, or we're using the shell method in order to approximate that volume. All right, next example. I think I will stop the video here and continue on in a separate video to show you the next example.